Okay, good evening. What we're going to do today is to spend some time to discuss homework number 2. And we will finish dynamic programming. And hopefully we have some time to review all the material or the question you may have before our midterm next week. And also I already assigned homework number 3. And it will be due also Wednesday next week. Unfortunately, I cannot give you feedback before midterm. I mean, one way we can do, again, we can discuss, is that we can set a deadline one day early. That means that you submit on Tuesday, then I will try my best to grade all of them before your midterm. Right? I mean, it's not mandatory. So if you submit this on Tuesday, then I will grade them before the midterm, which is evening on Wednesday. And all tests will be an open book. The only requirement, I ask you to open the window, right, so that I can see you. And open window means that you turn on your video and try to set up your window a little bit away from you so I can see you. And after the test, you are required, so because this is the first time I do this kind of test and ask you to submit immediately. So what you can do is that you take a photo of all your test sheet and send me through the Canvas. On the safe side, you can also send me an email. Right? I will set up some kind of deadline, maybe within 15 minutes or 30 minutes, and then you submit all your sheets through Canvas. I don't know how long did it take for you to upload all the sheets through Canvas. We can discuss. So what do you think? How many minutes do you need? Or do you have experience, or you know how to upload?
I think 10 minutes on the safe side would be best, just in case something goes wrong or in case the upload is slow.
Okay, so how many minutes you need?
I think 10, it's like the worst case.
Oh, 10, yeah, that's fine. And also on the safe side, if you want, you can send me at the same time the email copy, right? So in case anything wrong with Canvas, so you can send me, that's also a record for you. Any other discussion before we discuss the homework about the midterm test?
Sorry, did you mention if it was open note or not? I must have missed that.
Yeah, it's everything open. Obviously, you're not allowed to discuss.
And we'll have the whole period for it, or?
Yeah, it's a whole period.
Okay, thank you.
Yeah. I haven't thought about how many questions I will give you. It's a challenge because you're working on the time constraints, and environment could be like stressful. So I want to make sure that you should have sufficient time.
Professor, are the questions going to be similar to textbook questions?
Yeah, but probably it will not be that difficult. I don't know. Because some of these questions, the textbook is like hit or miss, right? And obviously you can search on internet, you may find it. You're lucky for the homework, but for test, probably you will not find it. So I want to make sure that you have enough time. Any other questions? If no questions, I will spend some time at the end, right? Just to make sure that you.
Sorry, I have just one quick question. Do we have like any sort of midterms from previous years that we can use as practice midterms for this one?
I don't know. Did I post on the previous website? If not, let me see. If I find the one, I can send you copies.
Yeah, just so that we know like some kind of difficulty.
Sure. I mean, it's a fair question. So if we don't receive it, probably, unfortunately, it's in the, if it's available, it's in my computer in Temple. I usually go on Friday. So you can send me a reminder by noon Friday, then I will send all of you a copy. Right. Okay, any other questions? Oh, I don't know what to.
Professor, I had a question.
Yeah.
So the extra, the 10 minutes which will be given to upload our answers, will it be extra? Like
Yeah, extra, yeah. Don't worry about time. I usually give some extra time.
Okay, thank you.
Yeah, so it shouldn't be an issue about time. Okay, so let's look at homework. Right? So homework number 1 and 2. Oh, sorry, number 2. So we look at the one by one. The first one is just recursion. I think most students did it all right, except a few cases, because we asked you to do using 3 different methods. One is you guess a bound, right? You build some kind of tree structure, and you guess a number, then you prove by induction. Then at the end, I ask you to prove using the master theorem. So just let you know that for the first question, it's relatively easy. So this one is relatively easy. And then you can use the master theorem. And for the second one, unfortunately, this one, master theorem doesn't apply. So it's a very important lesson. I know that you learn master theorem in the program technique. You know, master theorem, there's a gap. So that means not for all cases. There's some cases you cannot apply master theorem. Okay, so that's the thing you have to remember. And then for the first one, I just want to show you. Let me see, I need to. Right now, I'm not sharing the screen, right? Sharing screen or not sharing screen? I don't think, no sharing, right?
No, yeah.
Not yet.
No sharing. Okay, that's good. So I'm going to write on the this board, right? The board to show you what's this the problem. The problem is this one is n squared. So, oh, I think there's a 2. So what you can do is just like a substitution. So Tn, so mainly is this one. So first term is n squared, the second term, right? So it's n divided by 2 squared, but there's a 2 here. And then the next term, you just repeat. So in this n divided by 2, then now n divided by 4. Right? But then this one, you need to multiply by 2 again. So it's a 4 times n divided by 4 squared. So you already kind of forget the idea. So that means there's a number, this is 2, and inside 2, the 4 and 4. Next one is 8. Then you can do is n squared, right? N divided by 2 squared. You just calculate it out. N squared divided by 4, and so on. Then this is n squared 1 plus. Oh, this sequence is very familiar, right? This is very familiar. This is the geometry sequence. So
Can
the
you
reason,
shift the camera to,
oh,
it's cut off a little.
can you see now?
Yeah.
Yeah, okay. So you know that the purpose I gave you this one is try to see if you can do this geometric sequence. So we know this one is just equals less than 2, right? We know this is actually is less than 2. So by this you know how to do it. Then you can guess, and this is the number, right? So you can put the C there. Then you can do induction. So all students can do it correctly. The key thing is that this is an order of n. That's the order. So that's the first question. I think almost all students did it correctly. Any discussion? No, right? So it's simple. The second one is a little bit tricky, right? So I think most students did it right, but some struggle in the sense that it's a little bit, you have to look at cases. But if you look at this equation, it's very simple. You can see that this is stuff on 1 over n, then the 1 over n minus 2, 1 over, so it's something like that, right? It's very easy. And now many students get stuck. What are you going to do this one? It depends on this value of n, right? So n, whether it's even and odd. So that's the key. So whether this is a 2k or 2k minus 1. So this is n. So you have to separate this kind of situation. So that's why you have this kind of expression when this is a 2k, then it's relatively easy. Right? Or then another case is that if it's 2k minus 1, then this is a 1 over 2k. Is that correct? Yeah. So that's easy, right? You can see this one. So you have to separate these two cases, even and odd. But for this one, and so how do you do it? In some sense, it's easy because this is take out the 2, 1 over 2. Then this is the sequence of, sorry, hard time to write. Can you see that? Yeah, you can see that. But this sequence, this is important. This is a harmonic sequence. Harmonic sequence. That's another famous sequence, harmonic sequence. So it's a 1 over 2 harmonic sequence, K. You're correct? Then how about this one? Actually, there's an easy way to calculate that. Because if you add these two together, so what you get, then that's the whole sequence from 1 to 2k, right? So it's a harmonic sequence of 2k. Is that correct? Yeah, harmonic sequence of 2k. So this is equals harmonic sequence of 2k. But remember, this 2k is this sequence add this sequence. So you need to subtract that one. So that's the one. Okay, so I know that a couple of students study very hard. I think one student told me that he spent hours to calculate this one. But if you have like a simple way to calculate, it's very easy. First you calculate for the even number, you already get half of the harmonic sequence K. Then we calculate this one, you don't even need to do anything. Add these two together, then it's a sequence, harmonic sequence from 1 to 2K, right? Then it's a 2K harmonic sequence, subtract this portion. But this portion we already calculate, that's all. Then you can just plug in the harmonic sequence equation. That's a standard. Right? So it's a log K or something. But it doesn't matter, it's just different by, if you have a log 2K, log K is the same order. So it's just you can get that, it's an order of n, log n. Right? So once I get the order of log n, then you can do induction process proof. But this example, you cannot calculate using the master theorem. Okay, so that's the end for this. Any questions? All clear? Right. So I think that's the easiest way to do to solve this one. Now let's look at a couple of questions. So there's some interesting questions. I think the best way is go through sharing mode of the text. I want to show you the text. I haven't done the sharing mode yet. I want to see what pages. Is it divide and conquer? Page, yeah. Page 260, 246. So let me see where's the sharing part. So I need to share the screen with you. Okay. Then 246. Yeah, that's the one. So let's look at some of the interesting problems. Right? So let's first read this problem. Is it a 1, 2? And now I forgot which questions we did. Oh, 1, 3, 5, 6. Okay, let's first check question number 1. 1, it says you are interested in analyzing some, it's like a big data, how to obtain data from 2 separate databases. Each database contains n numerical value. So there are 2 n values total. And you may assume that no 2 values are the same, so they're all different values. You like to determine the median of this set of 2 n values. So that means the middle value, middle one, which you will define here to be the n's smallest value. You have 2n and n. However, the only way you can access this value is through a query to the database. In the simple query, you specify a value k to one of the 2 databases, and then choosing the database will return the case smallest value that it contains. So basically, you have 2 databases separate. And then you query say, I want the case smallest value, you return. And since each query are expensive, so you would like to compute the median using the few query as possible. Give an algorithm that find the median value using at most log n query, right? So that's a restriction, means that you are only allowed to use. So how you solve this kind of problem? Although many students already know. But I want to discuss with you some of the idea. That's more important. So basically, you have a 2 database. You can see, right? So you can just imagine that these are the one. All these are sorted already. So you can imagine these are kind of sorted. So that's the smallest to the largest. Right? So you have n here and n here. So what you're going to do, so that's the key, right? So you want to find the nth element. The challenge is that the fact that these are sorted is good, but you don't really know the relative value of these two. You could end up with some situation that this one left one is all very large number, and this one is all very small number. So you cannot really say that which is which in the terms, n's, right? So this one is very much like the problem I discussed with you. It's not discussed in the book. It's about the searching, right? Searching and elimination, or like a binary searching and eliminate, divide and eliminate. Remember that example, divide and eliminate. It's the same idea. So the key thing is that you do the query in the middle here, and this is middle. Key is middle. Then you want to see the value of this one and this one. You value the middle one and middle one. So you want to see whether this one is larger or smaller. Right? So if this the middle one, so that n minus n divided by 2, if larger than that one, you can eliminate this portion. Why you can eliminate this portion? It's the same idea. Is that since this one is larger than this one, right? So this is smaller than. So it's safe to eliminate half of this one. And all these are sorted, and this is larger than that. So in other words, all you need to make sure that whenever you eliminate something, the nth smallest element is not in the part that you just eliminate. So that's the key. Okay. So that makes sense, right? So this one will never appear in there because this one is already larger than that. So then you use the same strategy. Strategy means that now you remember you eliminate the what? Half of this one. So the next things what you need to do is find the n divided by 2 remaining one. So then you can just repeat the same process. Imagine this one you already get eliminated, and you get only half of this. So this is only half, this is the n. So what you're going to do, you use the same strategy. But this time, what you try to do is you still do the two query. One query will be half of, is this one. It's still the same. Half of this one. Right? I mean, this is n divided by 2. This is also n divided by 2. Oh, sorry, it's not n divided by 2. It's n divided by 4. Yes. This is n, or this should be half of this one. So it should be divided by 4. Right? Is that 4? Yes, divided by 4. Because initial one is n divided by 2. Next one, n divided by 4. Then you just repeat the same process. Depends on which one is larger. The smaller one, the portion, then you get another one. So at the end, you will get like this. Each time the portion they eliminate, get this eliminated, and they get eliminated. Then what you get is what? Is that the geometric sequence. Right? And you just repeat this whole thing. You add all this together is one number. At the end, this is equals A. Right. So each time you just reduce this side by half query. Although you don't really know, it depends on which value. So this one we cut a little bit more, this will cut a little bit less. So the idea is each time you cut half of the size of the previous check or cut. So that's the whole idea. So it's a very smart way. Now remember, this one also in some sense like the stingfish problem, right? So you give this a range and how you should set up the time and what should be the next one. And you sample, but each time you sample something, you cut out, you eliminate a certain portion. So this is a very important technique. And why this is log n? Because each time you divide by 2, so it's a log n step. So it's very fast. So that means you want to find the nth smallest element within 2 sorted sequence. You use only log n query to determine the middle element or median. Okay. So you should know this kind of technique. Just imagine that in the test, I can generalize this one, right, to see if you can adapt this kind of strategy to solve some extension. Any question we need to discuss? You all understand? Okay, so that's good. Then let's look at the next one. Next one, again, we go to share screen. This is number 3. Oh. This is also very interesting. Okay. Actually, the first 2 questions are the most interesting one. Suppose you are consulting for a bank that concerned with a fraud deception or detection, and they come to you with the following problem. They have a collection of in-bank cards. So you have an in-bank card that they're confiscated, suspecting them of being used in fraud. Each bank card is a small plastic object containing a magnetic stripe with some encrypted data, and it corresponds to a unique account in the bank. Okay, so each card has a bank account. And each account can have many bank cards corresponding to it. And we'll say that the 2 bank cards are equivalent if they correspond to the same account. It is very difficult to read the account number off the bank card directly. So you assume you cannot, otherwise you just check, right, to see if any 2 cards are the same number, a bank account number. But the bank has a high-tech equivalence tester that takes 2 bank cards, and after performing this computation, determine whether they are equivalent, means that they correspond to the same bank account. Their question is the following: among collection of n cards, is there a set of more than half, meaning n divided by 2 of them, that are all equivalent to one another? That means they all point to the same bank account. Assume that only a feasible operation that you can do with the cards are to pick 2 of them and plug them in into the equivalent tester. So you just all you can do is just a tester. You pick 2 cards and then you insert to the machine. You tell whether it's yes or no. I mean, match or do not match. Although they will not tell you which bank account number. Right? Just say this equivalent or not equivalent. So how to decide the answer to their question with only n log n invocation of equivalence tester. So the challenge is that you have n cards. And if you want to do pairwise comparison, I mean, every two, you can, how many possible n pairs? You have n square pairs. So if you can do a brute force way, you just test all of them. Right? Then you just draw an equivalent class for that. Then you can see whether it's you have a majority of them are fraud or not, less than majority. Right? So let's take a look of this problem again on that. So this is a really interesting problem. And so the key is that there, remember the question. The question is not asking you to say that whether there are two cards are the same. They say you have over half of the cards correspond to the same number. Let's just do a brute force one, which is n squared. So what you can do is that you pick a couple number, right? Cards, suppose 4 cards. So you can build a graph. Say it is yes, right? Then you can test this one. If this says no, then you say yes. See, you do this kind of test, and you may have test this one is no, or something like that. And then you test this to see this thing whether it's yes or no. If this is yes, then this is yes. And if this one says yes, right? Oh, but this is impossible. If no, this says no. But you have to do n squared test. So in this case, it really means that this test match this one, this test match this one, this test match this one. So they're equivalent. Right? So you know that these 3 cards are the equivalent, are in equivalent class. So let's just look at another scenario. Again, the 4. You may have another scenario. You say this is yes and this is yes, all the other ones no, 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 no. So this really means that these 2 cards are the same number, these 2 cards are the same number, or the other one different number. So you get that? So that's how you brute force you do it. You just do all this one, you construct like a graph, right? Well, actually, for the one that mismatch, you don't even need to draw a line. Then you find the largest subgraph, complete subgraph. Then if the set size of the largest complete subgraph is more than half of n, then you say that the majority is yes. So it's pretty easy. But this is too much comparison. Right? So imagine that checking the bank cards each time you charge $1. Then that's a little bit too expensive. So what you can do is that they want you to do it n log n, so which is much smaller number. So what we're talking about, this is talking about if it's n is 1,000. So this is like 1,000 squared, so it's very big. This is an order of 1,000 log 1,000, but it's a much smaller number, right? So that's the idea of you want a much easier solution. Okay, now let's see. So it turned out this problem is very much like the celebrity problem. Remember the celebrity problem is that we first do elimination. We eliminate. Then after that, we verify. But so what we eliminate? Remember, celebrity problem is that you ask a question about 2, you eliminate one of them. So you can do the same things. All right, so make it simple. We assume that the total n is a 2k. So I just gave you an example. The easy way is the example. Okay. Okay, what this really means that you have like a card, right? So this one, I just want to distinguish this one, really means this one potentially be a majority. And you may have like this scenario, these two cards is the same, right? So you do this kind of comparison. So this is a group and group and group, group and group. All right, so the key thing that they say that whether this guy, a particular one, like this one has a more than half, number of one is more than half of that. So that assumption is very important. Half of, more than half, or equal half. So when you do this kind of comparison, you have only two scenarios. One is that mismatch, right? Mismatch, and one is a match. Right? So what you can do is that if there's a mismatch, you just eliminate the whole things. So you eliminate the whole. This is a. Let me see. Yeah, this is a good example. So you eliminate, you take out the whole things. But when you take out this whole thing, you have to remember the fact that if you take out a pair that do not match, and you take out the worst case, you have 1, 1, right? You may have other things, and the other one cannot be 1. So that means whenever you take out one from this majority, and another one is anything else. So each one, this one would, I mean, it's like a 1-to-1 matching. So whatever left, still, if this one is still the majority, and this one is still the majority, right? And then when you pair 1, 1, 1, 1, all this is the same. Right? So for all the ones that equal, you eliminate half of them. You eliminate half of them. Again, for the same argument, right? So that means we assume the number one is already half or more. The one that form the pairs, the ones that for ones that's supposed to be majority, still have a majority in terms of pairs. Then when you eliminate this one of this, you have two, a pair. Whatever left in this case is 1, 1, 1, right? You still maintain the fact that this number one is the majority. So that's the key idea. So you're doing this kind of elimination. You want to make sure the property for that, which is number one, is half or more than half of the total size, the number. But so in that way, you do it very quick. You see this through example, you can see that one, right? See, quicker means that you can eliminate very quickly. Because you not only eliminate one from a pair that match, you eliminate lots of them that do not match. So each time you eliminate one round, you eliminate at least half. Most of the case, more than half. Extreme case, you can eliminate all of them, right? So let me just show you the example. Suppose you have this scenario. Okay, I think all this you need to look at some example and you get the idea why this is correct, right? So obviously you need to see that you have like a 4, 1, you have 3A, you have 2B, whatever, right? 2D, 3B, and 1D, 1A. It doesn't really matter, right? So the one that the mismatch, you will cross, take out, take out, take out, take out, take out, right? So it's very fast or eliminate. And you get this lucky one, this one, and you take out this one. See that in one round, you already eliminate to only one element. So this is like a celebrity problem. That's the only one possible have this more than half or half more than half of all. But this is a good example to show you that you still need to verify, like a celebrity. The fact that you survive doesn't mean you're a celebrity. It's the same. The fact this one survived doesn't mean that this has 50 or more than half of the percentage. So then what you need to do? Then just the same like a celebrity. So you pick up this card, compare with all the other ones, but that's linear. Right? And so now you get the idea why it's n log n, because each time you eliminate at least half of them. So each time you eliminate half, right? So that's why you have a depth of log n and then times n. Right, so it's n log n operation. Is that clear? I don't know. I think most students did it correctly, but I don't know. Maybe there's some answer. They also answer correctly, meaning that whenever there is a matching, then the one that holds the majority will still be the majority. But you need to know the fact why this is still the majority. Right? So the key thing that when you eliminate those mismatch, worst the case that you have half of them is the majority one. So whatever remaining one, the one that original the majority is still the majority. Right? Then we eliminate half of this one matching pair, you still get the majority. So that means through this kind of process, the one that as a majority will still keep the majority. Right? But not the other way around, means that the fact that eventually one survives doesn't really necessarily mean that that will constitute a majority situation. You have to verify. So I thought this is a really interesting problem. Right? Any question on that? You all clear? All right. Okay. Good. So now we can do one more. The next two questions is kind of interesting. Initially, I saw that I probably made a mistake. The number 5, and then the numbers. What's the number? What's the other number? Number 6? Yeah, no. Okay, so number 5. This is like a computation geometry problem. So basically you have, it's called hidden surface removal problem. This reminds me, there's another problem called city skyline problem. So basically it's a linear expression, right? Y equals AI x plus BI. Then you want to see that you have many lines, right? You can draw on a 2D surface, like this example, 1, 2, 3. Look at this. Right? Then if you're standing up, way up there, like what I point, you look it down. Then your eye will see certain line section. So what you want to know that whether those section you can see at least for each line, you can see certain section. If all hidden, then that means this line is totally hidden from you. So what this really means that, look at this one like a 2. You see the section of a 2 is all hidden, right? So like this section from, so by the way, every 2 lines you have one intersection. You can see from the left of 2, intersection with 1, this section is totally hidden by 1. And then start from here, right? This section from this one to this one. Actually, you can go all the way. It's all hidden by number 3. Now they ask you, give you a bunch of those lines. How do you find out which section or which lines you can see at least portion of the section? In fact, this problem probably is too hard. I have to admit, unless you find it the internet, right? Because this could be, it's not so obvious, a simple homework exercise. I don't know why also give this one. You may take 1 semester or 1 year to solve this problem. So it turned out the key thing is the angle. The angle really means that the angle between the, suppose you have x, right? Then you look at an angle between, for example, 5 and x, so you have an angle, this angle, or slope, they call the slope. And slope can be positive. So that means this, from x point to 5 is a positive. Some of the slope could be negative. So negative, like a 2 is a negative. So that means, then what they do is that they first use a sorting algorithm to sort those lines based on the slope or the angle. Then they do a divide and conquer idea. So I'm not going to go through this is because I think all students did it right. Maybe they find some solution there. So the idea is from this example, you can see that the section from 1 is this portion to the intersection of 3, right? Then from 3, this section is from this point to the intersection from 3 and 4 is this section. So you can visible. And then there's another section from 4 intersection with 3, then all the way to the intersection of 5. Then there's another one is from this all the way to the top. So these are the like a sequence of sections. So the idea is that suppose we sort this one, then you do a divide and conquer in the middle. Then all you need to do is just merge those sections. It turns out that you can just find out their intersection. Once you find the intersection, a left part of one will be removed and the right part of the another one will be removed. Then you merge this one. So it's basically you do a partition, then you merge. So just like a merge sort. So eventually you find all the sections that you can that are visible. So to me, this is not that exciting. Not the fact that it's a difficult problem, but it's just too hard. So I'm not going to go through that. Instead, I want you to look at this one. This turned out to be an interesting one. But also the problem is not that exciting in the sense, let's read this one. So consider the n node a complete binary tree. When the n equals 2 to the d, right, for some d, and each node, the v of t is labeled with a real number. So that means you have a weight, whatever. And you may assume that the real number labeling of nodes are all distinct, they're all different. A node, the v of t is a local minimum. So each node has a label. If it's local minimum, if it's less than the label for all its neighbors, right? So you're given such a complete binary tree, but labeling is only specified in the following implicit way. For each node v, you can determine the value of xv, means that give you a v, you know that what's its value, right? Then show how to find a local minimum of t using only log n probe to the nodes t. Right. Okay, so let me, again, I think the best way to draw on the board, so you know. I thought this problem is not relevant to the chapter for the reason is that it has nothing to do with divide and conquer. And the problem is not that particularly exciting, but let me just show you this. Right, something like that. This is a complete binary tree. Then each one has some kind of number. Let's assume this, whatever, 6, 5, 4, 1, 2, 7, or something like that, right? It doesn't really matter. I think most students did it correct, but so they start from the root. See, if this one, you see the challenge, you immediately know there is some problem with this one. In some sense, all the problem give you with the complexity already. So in some sense, they already give you a solution. Why is that? Because normally when you do a tree search, like this one, right? This one, you start from this one. This one is larger than 2 of its children. Then you have to search left tree and right tree. So you can imagine this is kind of recursive. They immediately say, oh, there's no way you can limit it to your operation to log n. So it's order of n. Right? So the fact that it's log n, so that means that this problem is kind of unique. In fact, this really means that if you start with this one, you can go along any kind of branch as long as this particular branch satisfies some simple condition. Right? So that's the one. So that means there are many solutions. So the solution is this one. If this is larger than, so that means you should argue this way. If both of 2 children are larger than this one, then the root is local minimum. We're already done. Otherwise, that means at least one of them are smaller, right? In this case, both are smaller. Then what you need to do is simple. You just say that you randomly pick one of them. It doesn't matter. You can pick around 4 and 5. Okay, 4. Then you repeat the same process. So the fact that this one, so this is larger, right, than this one. So you treat this one like a root. Then you continue the same process. So in this case, not both of them are larger. Otherwise, this will be local minimum. So you go down to this one. And this will continue, right? So this will continue. To see if this is a local minimum, means that if both are smaller than this, are larger than this one, this is local minimum, we're done. Otherwise, this must be smaller. Say this is a 0. Then you go down. When you go to the leaf, already done, because that leaf node must be the local minimum. So in other words, no matter what happened, the worst scenario is from root to one of the leaf, right? So it will stop in the middle or stop at the leaf. So this kind of problem is interesting, but it's at the same time not interesting because there are so many, if you follow any kind of branch. So I'm pretty sure you can do exercise. If you follow the branch of 5, you can do the same argument. So potentially that means there are many local minimum, right? So to such an extent, you can relax the searching strategy. You don't have to exhaustively search all of them. You understand that? And also, I don't know what happened. Maybe the way the problem is given so confuse you, or maybe the way that we teach data structure in such a way that you think that everything tree should start from the root. In fact, the best solution for this one is not from the root. I mean, root is still correct. You can start from any arbitrary node, any arbitrary node. You can start from any nodes. You say that you can find any nodes. So this you should learn that. So that means you can randomly pick any node, interior node, outside node, leaf node, root node. You apply the same argument, still correct. You get that one? Right. So that's why I'm a little confused about the question. The way the author gave a question and say the complete binary tree. Actually, in fact, it doesn't really matter what kind of tree. you can draw a tree like this, right? So you don't have to be a binary tree. It doesn't really matter. You can have any kind of like this kind of shape. You get that one? Can be any tree without any direction. So you randomly pick a points and randomly pick a points. If all of the neighbors are larger than you, then your local minimum. Otherwise, pick a branch that has corresponding smaller number. Say do the same argument all the way to reach one of the leaf, and you stop. You get that? Right. So this is more general solution. Okay. So I spent lots of time, but I think those are more important than I teach you. Okay, so let's stop for this one, but I want to give you some exercise in the sense that I want you to do more, which is more exciting. Can you see it? I'm sure you can see it now. Or we can look at the slides for today. So this is what we learned last time, and it's very important. Oh, what happened? Right, those principle. So principle means this principle called Persimmony Theory. Means that if you develop something, right, to build some kind of theory, whatever theory, like for example, curing theory or some theory, if you have a two theory that can explain the particular phenomenon, and you always pick the simple one. And the same thing, if you have, give you a problem, if you have a multiple solution, you always find the simplest solution. And same rule apply the proof. So you have a many way to prove something, like your algorithm is optimal, whatever. You always pick the one with the simplest one, intuitive one. So that's why it says a good theory exhibit some quality with a good theory that is beautiful and natural. It's a very natural one. So I last time mentioned that the two paper. So if you have time, although this is totally outside the scope of this class, so you can take a look because it's very simple. Both paper, no mathematics involved, but explains something really, really deep. Okay, so let me just give you some more interesting problem. So there are two problems. One is simple, the other one is more difficult. The first one you can think probably most of it already can solve. But if you solve it after the break, you can tell me. So you imagine that you are living in the village. Your village is a house connected, all connected through internet, right? So you can imagine those are the village. And you have an in-house connected using cables and switches. So all the nodes, interior nodes are the switches. Non-interior nodes, you can say this like a leaf or root, whatever, are the house. Right? So interior nodes are switches. So you assume that for each connection cable, you have a length, right, cable. Now find the two houses that are the furthest apart in the connection. How you find the algorithm? Very quickly. You can apply, say, okay, Dijkstra, whatever. If you, I mean, the intuitive way, not intuitive, naive way is that you compare pairwise house distance. Then you will need at least n squared. That's really too expensive. We forget about even the calculation between two houses, the distance. You have lots of repeat calculation. In fact, there's this linear algorithm for that. So how you find the linear algorithm? Linear algorithm that if you have n house, you need only n step, or c times n steps, to find the two houses with longest distance. So it's not shortest distance, it's longest distance. And Then the question is that suppose you come up with an algorithm, how you prove your algorithm is optimal? And there's a very nice algorithm for that. And the proof is even more interesting, how you prove that. You find two houses that furthest apart. Remember, those houses are the non-interior nodes. Interior nodes are switches. Right? So you can imagine like the diagram in here. You see this diagram? Oh, diagram. So I put a house with a small square, really means this is a house. Right? So those are the outside one. You have five houses. Right? Then there's switches. I don't specify what kind of a tree. It could be a binary tree, canary tree, any kind of trees. Right? So there have 3 switches in the middle to connect those houses. Okay. Any discussion? Or you can think about, or if someone can solve it, we can discuss after break. So the second one is more interesting, but it's a little bit harder. But surprisingly, I make it easy. In fact, you can find a linear solution for that also. Actually, this is the result out of one of my research. There is an interesting story. I have first one of the master students to solve it and publish, and lots of references, citation. It turned out to be wrong. Then I asked another student to solve it, and she solved it, but still wrong. So at the end, I tried to think a little bit more and find a real solution. And this solution turned out to be very simple. So the problem is this one. It's a very exciting problem. So it's like a house allocation problem. Really means that suppose I give you certain number of houses, right? Like 5 houses in this one. And you have a population of, say, 8, in this case, 8 people. Now the question is, I ask you to assign these 8 people to different house, right? So you get that? And you assume that each house has some kind of capacity limit, right? So for example, this house can host up to 4 people. This house can host up to 3 people. This can be 5 people. This can be up to 2, and it can be up to 2. So as long as you allocate whatever the number of people does not exceed this capacity, you're fine, right? So it looks like this is not difficult. The difficulty is this one. So it turns out that these people like social. It's like a COVID situation. They like to make a phone call. The phone calls means that at that time, old time, is a pairwise phone call. Means that you have 8 people, you form different kind of pairing. Means that they can simultaneously make a phone call to different people. Right? Or you can even phone call to the same people in the same house that does not occupy any bandwidth requirement. Right? So let's look at one scenario. Okay, you have allocate 2 people here, 2 people here. You have 1 people talk to this people, another person. So I draw a line here. Then the second person make a phone call to a guy somewhere here. So that's why we have another line, right? And this second person here talk to a person in this house. And this one, the second one talk to another one. So you can see that whenever you make a phone call, you put some kind of bandwidth requirement on the phone line. Right? So it depends on this kind of pairwise pattern. So you may have a different kind of stress on this link. And assuming that the link, each link has some kind of capacity limit. For example, this one say you have a 3 capacity, really means they can support up to 3 phone call. This can be 5 phone call. Right? Now the question is that it's really interesting. Really means that not just assign people to different house to meet the limit of household limit, right, the size, but also these people will talk, and you don't know really what kind of pattern, just pairwise call. And you have to look at the worst case scenario, right? So that each link will not be overloaded. Otherwise, you have this kind of scenario that the situation is bad. Right? So another question that give you this configuration in terms of bandwidth limit and capacity limit of house, and you want to host n persons. So the question is, can you allocate in a way that you meet all this requirement. So let's just look at another scenario. For the same case, like a 2, 2, 2, 1, 1, right? You may have another pattern of phone call, like this two person just talk to each other, so you don't consider any bandwidth requirement. But these two people want to talk to one guy here. You can see that different kind of pattern, you have a different stress on the phone link. So make things more difficult is interesting, is that I'm not just ask you to allocate to meet the current requirement, but also future growth. We call this a maximum elasticity. Really means that suppose those people, like married people, they may have a children. Right? So they will have a 1 child, 2 child, or whatever. But whenever they have children, so we say that the capacity grow, right? For example, if a 50% growth really means that each household, the growth in terms of population is increased by 50%. Obviously, when you increase the 50% in increased capacity, you make sure this household can hold this 50% more occupancy, but also the link capacity should also meet. Now the question is this one: can you assign something so that it will support the maximum elasticity for future growth? So it looks like this is a very difficult problem, even harder than the Dijkstra algorithm, right? Like more than shortest path. But it turned out, as I found out, there is a very nice algorithm to solve it. So just for your thought. Right? All right, but the first one you should be able to solve it. We can discuss later. All right, so I think I'll carry away a little bit too much. Let's quickly review what we discussed last time. Right? So that's the key. So what we discussed is this paradigm of dynamic programming. But we discussed this already. So I think I directly go to this idea. The dynamic programming idea is that you have you want to divide a problem into a set of sub-problems, but different from the divide and conquer. So this may overlap. Right? So you may have also a sequence of problems. It depends on the problem nature. So we summarize those techniques is like you can divide a problem into like a linear sequence. So like a weighted interval schedule last time we mentioned. And so you keep on adding the schedule at a time, then you have a binary choice, either select or not select. And then in some cases, you may have to multi-way choice. So we look at later, is a least square problem. And in some cases, you want to make a problem more general by adding a variable. In this case, a knapsack, in terms of the weight, by adding a variable for weight. And then you may even consider a new sets, like pair shortest path, or pair shortest. We haven't discussed that. And today we'll look at another one. We discussed a sequence of matrix multiplication. So you have to solve all the sub-problems. And then when we have time later, after break, we'll talk about some of the bioinformatics problem, RNA secondary structure. And one important thing is that when you do this recursive call, you may waste lots of space. Recursive call is efficient, is nice for problem solving because it's a very natural way of thinking problem solving, but it's not efficient because some sub-problem may overlap. So you have to use memorization, and in the best case, you're doing iteration bottom up. So that's the. So let's quickly review, right? So for the interval schedule, remember we talked about this one. So you have a set of activity. So the key thing is that you want to put as a linear order based on the finishing time, right? So the whole idea is that you start from left to right, right? Whenever you add one extra activity, you think about binary situation. Is that either you select or not select. But the difference now you need to find the maximum weight. When you select, you need to add a utility of this weight. So this is the solution, right? So probably I'm not going to go through all these details. The key thing is this recursive expression. Is that suppose you're considering the J, so you have two choices, either you select J or not select J. If you don't select J, then the best solution is from beginning, which is left, to J minus 1. So that's how you get the J minus 1, right? If you don't select J. If you select J, then you need to add its weight, right? That's a utility value. Then where's the stopping point? Means that it's equivalent to a notion of this PJ. PJ means is the last one with the largest index that is still compatible with J. So in the previous case, it's like if you consider 8, consider 8. If you consider 8, you cannot consider 7. We cannot consider 6 because they not compatible, right? They conflict. The closest one is 5. So it really means that if you select A, you include this utility, then the problem is reduced to find out the best schedule from 0 to 8, right? So that means from 1 to 5. Because 5 is the last index that is still compatible with 8. So by this, you do this similar like divide and conquer, but it's just a simple problem.
Professor, why
Yeah.
P8 is not 3 in the previous case?
Which one?
In the previous slide,
Yeah.
P8 should be 3, right? Because
P8, no, P8 is a 5. Why is it 3? 3 ends here.
oh, it ends here.
Yeah. You see, look at the ends, right?
Yeah.
But 6 and 7 cannot be included, right? So it's like it's similar like divide and conquer. So now the problem reduced to if we include A, then the rest just consider the best schedule from 1 to 5 in terms of total weight, right?
Oh.
So all the thing is that this kind of recursion is that you have a larger problem, you reduce to a smaller problem. Then it will end, right? So when J is a 0, that means end. So not that simple, right? Then they just recursive call. Now all you need to do just like you write the recursion, right? Recursion and recursion. But unfortunately, there's a problem for this one, as we mentioned, like this kind of example, very much like a Fibonacci number. Remember, Fibonacci number is that the number equals to the previous number, you add together. Now you can see that if you want to do 5, right, 5, if you select 5, then you have two scenarios. One is that you don't include 5, then it's the best one is from 1 to 4. Very simple. That's why you have. Or include 5, then you cannot include 4. Then it's equivalent to your utility of 5 plus whatever utility from 1 to 3. So that's what we call 3. So this notation really means like a 2 recursive call. Then 4 depends on 3 and 2, right? You see, 4 depends on 3 or 2. 3 means that if you don't select 4, you basically start from 1 to 3. If you select 4, 3 should not be included, only include 2. So the same argument. So it's like a Fibonacci sequence. But the problem is that you see this 1 and 2 and 3 appear multiple times. So it's a lot of waste. So how do you do that? You use memory. Very simple is that for each number, you put the initialization empty means that initially is not initialized. So when you call, recursive call, you first check if it's empty. If it's empty means that it has not been calculated before, it have never been initialized. So if it's not empty, if it's not empty, it means that you don't need to calculate. You don't need to go through recursion. You can just directly return the value. So that's the trick. And even better one is that you can totally eliminate the recursion. You can do the iterative process. Just like a Fibonacci number, you calculate from 0, 1 to 3, right? So the same idea. So you can do this way. This is the iterative way. You just need to be very careful when you do this way. You follow order. Right? So in later example, we all see follow order from 1, 2 to n. So that means you have a sequence. Right? You do sequence, from left to right. So that means when you calculate a later number for mj, which is a large number, it depends on the other m value, but it's a smaller j value. So it's already calculated. You see, the whole idea is that you start with a small solution for the small problem, then eventually you solve the problem for the larger one. At the end, when you reach n, that means you find a solution for the whole, right? And this one we mentioned last time that this is very much, the recursion is very natural. So that's why it's like when you code the program initially, you tend to use a goto statement. Then there's a famous Dijkstra letter in 1968. It says goto statement considered harmful. It's the same idea here. For different reasons. Goto statement, too many, then we call spaghetti code. It's difficult to read. And so that's why you have a structured programming. And the same thing here for different reasons is that if you have too many recursive code, then it's not efficient, it's slow. So you use the iterative solution, it's much faster. Right? Then we talk about the least square problem. It's very similar. You know the least squares, you find a line so that the distance between the line and all the points is minimized. Right? So there's a well-known result, how you calculate to give you points, find out the line position is a straight line. But if we relax the problem, if we allow the multiple lines, but there is a penalty. Whenever we introduce a line, there's some penalty. So what's the best solution for that? Obviously, there's a trade-off between the cost for adding one line and the error, right? Error means a distance between those. So it turns out you can do it, it's a very similar one. It's a sequential process, sequence. So basically from left to right, you want to match. So at a certain point, you need to decide whether you should continue with the older straight line or you add a new line, right? So it's a very simple recursion, right? So recursion is this one. And suppose you are the j, right? The j towards the right. Then you need to find the position before that is I. And the question is which I? Right? Suppose you want to introduce a new line for that. So it all depends on this the error between I and j, right? Square root error, plus the cost of adding one line. It also depends on the position of I. They need to find optimal solution for this I minus one, right? Before that. So that's why it's kind of recursion. So all this one, the same idea is that you have a large j index and you call for a solution, same problem, but smaller index. So that means this recursion will end correctly. Obviously, when you do this one, you don't need the recursion, you can do iterative process. So this is how they do it. So I'm not going to go through this, it's the same idea here. So you just build a table. Table really means that those entries, right? From small to large one, so from left to right. Eventually you build up this value gradually. As you build up, fill out the number for these slots, then the solution for the later one depends on the early solution. So this is how you get this one. But it's a very straightforward. So you're adding points, very simple. Checking the error, square root error, depends on the pairs, right? Number of pairs. So I'm not going to go through that. That we solve the problem. We also solved that the knapsack problem, which is more interesting in the sense that you have a limit in terms of a weight. For example, you're a thief, go to a jewelry store, want to pack your bag, right, with most expensive one. But it also depends on weight. Unfortunately, you have a capacitive weight. And if this weight, it depends on the granularity of weight. If all this granularity is very small, like a dust, then the optimal solution is very easy. Just find the items with a maximum ratio of value divided by weight. Right? More variable, but less weight is ideal. Right? But the problem is the granularity can be large, then the problem turns out to be a much harder problem. It's an NPR problem. So the solution is more interesting in the sense that instead of solving this problem for a particular weight, we try to find a solution for all weight, just like a Dijkstra algorithm. So that's why we have introduced this concept of a different weight limit. So this also is kind of recursion. And so I'm not going to go through that. That's quite simple. It's whether, again, for the item, whether you select or not select. But this one has a kind of two parameters. One is an index subset, and the other one is a weight limit. So it's two. So it's a little bit more involved. It's like a two-dimension dynamic programming. But the key thing is how you introduce extra variable to make the problem more general. So that's the. Then once you have that, you can do the iterative solution. Iterative solution, you have to be careful is that you want to find a solution from the smaller space, means that smaller weight, and also the index for the subset from small to large. See, that's why you see this loop. Right? The loop is from small, I, weight also from small. Unfortunately, this problem is that we call the pseudo polynomial. Really means that it's not just depends on n, depends on the weight, but the weight could be sufficiently large. So that's what we discussed last time. I think we are almost run out of time. Yeah. And this is another example. I just stop right after that. And this is even another interesting, it's more involving sense that we saw the linear sequence, and we also case we add one variable. But this one is to try to find all subsequence, adjacent subsequence. So that's the idea. It's involved the matrix multiplication from 1 to n. The efficiency of matrix multiplication in terms of minimizing the number of multiplication is how you put the parentheses. So all we need to care is you make it more general is that you solve a problem for I to j, not from 1 to n. 1 to n is a special case. You want to find the solution for all I and j. And the I could be any position. And j, obviously, the distance to I is a k. K start from small one means that only 1 or 2, then 3 and 4, right, in terms of gap. So that's how we build up. It's like I call this pyramid. So you find the optimal solution for all the adjacent subsequence. And for this k value, this key means j minus I from the small, a little bit larger, all the way to n minus 1. So that means you include all the sequence, right? I mean, original sequence from 1 to n. And this one costs the n square complexity. So you see this two matrices for the reason that this one is calculate the value. The second one is basically calculate the position. So position really means where you want to put the parentheses, right? So last one, I think we're not going to discuss this. I think we can briefly discuss during the break, after the break. Okay, let's stop here. And we'll take a short break. We'll come back at 7 o'clock. Okay. Okay, so let's continue. By the way, anyone come up some idea for that extra problem? Or we can discuss after the midterm. So this is some, yeah, you find some solution?
No, I just had a question, because we had like circles, and I'm assuming that those are like switches, right? And the slide.
Oh, by the way, there's no circle. Oh, you mean circles?
Like,
yes.
yeah, like denoting the inner nodes, I think.
You know, inner node is just switches.
Yeah, those are
separate.
the switches, but then we also have like square and circle that are, I think, on the outer edges. So I'm not quite sure.
Oh no, this is just to explain. This one is like a house, so it's nothing else.
So the circle right beside the house, that doesn't represent anything. Oh, it's the same.
Yeah, it's the same.
Okay,
yeah, both. Yeah.
Oh, okay.
I just want to distinguish. These are the house. In the middle is a switch.
Oh, okay. Thank you.
So you find solution, or anyone find solution? Like how you find the two houses that are furthest apart in the connection. Oh, again, though, because we probably need to move on. Maybe we discuss after the midterm. Right? So it's a very interesting problem. It turns the solution very simple and the proof very simple, but it needs some time. Okay, let's continue with the material we're going to discuss, and we're finished today. So the last one that I think last time we briefly mentioned about, in some cases we have two solutions. One, in shortest path, you can have a Dijkstra algorithm. The other one is using dynamic programming. The Bellman-Ford is basically dynamic programming. But use some kind of extra one constraint is a hop count. Hop count means how many hops, intermediate nodes you use. So they introduce a notion called I. I means that they use I hops. And we all know that from the original one, like from S to T, right? T is a destination. You need a maximum n-1 hops. So you can do this kind of recursion call. And the general expression is that for each intermediate nodes, you want to find the shortest path to the destination. So that's the one. Really, you maintain the shortest path to to a particular destination for all the nodes. So that's give you an idea is that suppose you are V. How you find out your shortest path? So suppose that we say that we can increase this I value, means that the path can be one extra hop. Right? So either you can use the previous optimal solution, which use I-1 hops, or you can ask one of your neighbor. So that's the key idea, neighbor. If your neighbor's shortest path plus your distance to your neighbor, all this together is shorter than your current estimate, then you should update. So that's how you do it iteratively. So in general, there are two models. One is called pull model, the other one is called push model. Pull models is really like a recursive call. It's called pull model. It means that you want to find this one, you need to find out it's a recursive call, then how you get it. It's called pull model. So that means you calculate the other value only when it's needed. Another one called push model. Push model means that means you aggressively push your new estimate to your neighbor. So I'm not going to go through this one because initially this is not in the slides, but you just need to remember there's a Bellman-Ford algorithm. There's one advantage of Bellman-Ford algorithm compared with Dijkstra is in the Dijkstra algorithm, you assume that all the link value is positive. But in some situation, value could be negative. Negative could be more general. You may argue that how can the distance can be negative? Right? So if we're talking about physical distance, obviously there will be no negative situation. But in the real life scenario, for example, you want to make a certain move to reach your goal, right? And a particular move you may add positive value means that it's better, getting better. But in some cases, you may have a setback. But the optimal path in your life may not always moving forward. Sometimes you need to move backward. Just like buying some stocks, right? So you cannot be all like get a positive value. Sometimes you have a setback. So that's make it more interesting in terms of generality if you have a negative edge. Okay, so I'm not going to go inside. There's still another one probably you already learned, maybe in program technique. I just want to refresh your memory about all pair shortest paths. All pair shortest means you give a graph, you want to find the shortest path between any two pairs. So it's more general problem than the shortest path. So one naive approach, you can apply the Dijkstra algorithm multiple times. In fact, there is a better solution called the Freud-Warshall algorithm. Sometimes we call it just Warshall algorithm with complexity and Q. So the idea is simple. Again, you introduce some kind of intermediate nodes set from 1 to k. Right? So that's the key. So size of intermediate node, not size means particular nodes. So you label nodes from 1 to k, right? So you give them the restriction, like how many nodes you can use as an intermediate set. Then you increase the intermediate node sets size. That means you relax the constraint. And start from beginning means that you don't use any intermediate nodes, right, to reach from I to j. So how you can reach ij? Only when they're directly connected. Otherwise, they cannot. Then you relax, say that, oh, I can add 1 to see what's the shortest path, right? You get that? So it turns out the optimal solution is very simple. It's a recursion like this. So suppose K0 means that you don't use any intermediate nodes. So that means a direct connection I and j with a weight. That's simple. Now, assuming that you want to calculate from 1 to k. So again, you just look at 2 scenarios. Are you really going to use k as an intermediate node? If you don't use the k, then it's a k minus 1, right? So it's the previous one. Whatever the optimal solution for k minus 1 is from 1 to k minus 1. That's clear. What happens if you use k? If you use k, that means k will appear as one of the intermediate nodes. Right? Then you just treat this one as intermediate node, then you partition the path into 2 parts. One is from I to k, another one is from k to j. But the section from I to k will only use the intermediate node from 1 to k minus 1, right? You're not going to use k again. So then this problem is I to k subject to the intermediate node set of k minus 1. Then another section is from k to j also. You're not going to use k once more. So it's k1 to k minus 1. So in this way, you can just do it this recursive calculation. Actually, you can do it in a matrix multiplication, a special matrix multiplication. So you can represent this connection using adjacency matrix. The sequence of matrix multiplications is just like a dynamic program. Okay, so this is the. So I would like to spend the rest of 1 hour on some more interesting problem, 2 problems related to DNA. And this is a very important subject, although we're not going to, in some university, they offer course on bioinformatics. Everything related to like big data or streaming, or matching, and so on. So bioinformatics deal with math and software tool for understanding biological data, where data sets are large and complex, very large set. So we'll look at 2 problems. The first problem called RNA secondary structure. Right? So don't worry, I don't know the biology, but I just want to give you an interesting problem called RNA folding problem. So this problem uses a very interesting solution. is that you partition the problem, not partition means you divide the problem into multiple sub-problems as part of a partition. So let's see what's the problem. So if you know biology, so we know that this RNA have some kind of alphabet, A, C, G, U. So don't worry about what's the meaning of that. Right? So the key idea is that there's those alphabet. You have a string. So the string, you see this is a string G to A. So it's over here, star G. So there's a secondary structure, means that it's a single-stranded, so that it tends to loop back and form base pairs with itself. This is structure essential for understanding behavior of molecule. Right. So this really means that you look at the kind of pair. Pair means A and U and C and G. So that means A and U can form a pair. You have a straight line, right? You should have a straight line. Look at this one, straight line. So A and U can form a pair, so that means getting close. They're getting close and close. So you see all this pairing, right? Pairing A and U, C and G. Then you may ask that there are many ways to pair. So what's the natural way of pairing? So that's the problem we're going to solve. So secondary structure, again, some of this. First of all, they say what kind of things it can pair. One is AU, UA, CG, GC. That's all we already discussed. So it's called Warshall and Crick pairing. So don't ask me why that. It's just the alphabet with this kind of A and U can like a match. And there is some requirement. Some of the match is okay, A and U, UA, CG, GC, but their distance should not be too close. So it's also called no sharp turns, means the end of each pair are separated by at least 4 interval bases, meaning that if you form a pairing, their distance in original string should be at least 5, or at least 4. Right? And another thing that you're not allowed crossing, no crossing, non-crossing, means that it should be properly nested, means that if this pair, I and J, either I, J is nested inside K and L, or K and L is inside I and J. So you don't have this kind of scenario, means that there's a crossing. So I show one example. Right. So as I mentioned that there's many ways to do folding, right? For example, why not this A folded pairing with this U? Then the shape is different. Or maybe this A is pairing with this U, right? Or this A can pair with this U. Obviously, this A cannot pair with this U. Why is that? Because it's not separated more than 4. But this A can combine with this one. So it doesn't matter. It's just you want to do whatever the position you're pairing. The key is that you want to find a maximum number of pairing. So how many pairing in this case is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pairs. So in the biology, this is called free energy, total free energy, optimal total free energy. It's a little bit more involved, but it just say that it's approximated by number of base pairs. So this I and A folding really means that you fold it some way so that the total number of base pairs should be maximized. Right? So that means give you an RNA molecule B1 to Bn, find the secondary structure, means the folding that maximize the number of base pair. So it looks like a very complex problem. Look at this again. Again, CG, AU can pair. How you pair this one, right? So that you don't have a cross. Cross means that this line cross the other one. And also the pair, 2 elements should not be separate too close. It should be separate more than 4 or more. Let's look at an example. Like suppose we have this line. This is a legitimate pairing, right? Because you can see that this U and A, AU, CG, right? And the distance is more than I mean, the original distance in a string is more than 4. That's fine. So you have 4. But this one is not good. Why this is not good? Oh, yeah, this is a distance is less than 4. 1, 2, 3. Oh, this is 4. Why is this is less than 4? Oh, it should be more than 4. It's my mistake. It should be more than 4. So less equal 4 is still not good. So in other words, it's very simple. In some sense, you have a straight line, then you should have pairing. You see this kind of like rectangle, right? So that means the size for this left and right should be more than 4. The distance is 4. Do you see that one? And also it does not allow crossing. You see the crossing? Really mean that this G, C, and UA, you see, cross each other. It should be properly nested. So the crossing is really reflected here. You see, we have those 2 lines that cross each other. So you can have either properly nested or you have a sequential, right? So if it's a string is very long, just imagine this string very long, you can have another kind of nested. Now the question is how you find the optimal pairing. Optimal pairing, or maximum number pairing, subject to those constraints. So it turned out to be not too difficult. The only thing that we have to be careful is you have to generalization. Generalization means that initially you want to find out the best pairing, optimal solution from 1 to n. We already know what's our generalized. Generalized should be I to j, right? Could be any. Then you can require recursive call. So let's just start with a simple one. Suppose you end up, your last one is n, right? So n pair with one particular t. So this one, yeah. If you have this one, then how you solve it? What's the next possible pair? Then this one naturally, because of non-crossing requirement, you basically partition this space into 2 parts. One is from 1 to t, another one is from t to n, right? So t to n basically t plus 1 to n minus 1. So that's how you do it. You just recursively, you put this one, obviously position of t could be many, right? Then once you have that, you basically partition the space into 2 parts. One part is from 1 to t, another one is t to n, right? So that's the solution. So then the solution, it's not too difficult, is that you generalize to I and j, right? I and j, not to 1 to n, I and j. So that means from bi to bj, any subsequence, adjacent subsequence, generalize from 1 to n. Then you look at the I and j. If I is larger than j minus 4, so that means I and j is too close. So there's no, so it does not allow any turn, right? So that means you cannot form any pair. So you stop. Right? So you get that. If you're too close, your pairing is 0. Right? Otherwise, there another one is that again, you look at the last element, like a previous case. Did this one involve any pairing with any previous one, right? So it's just like how you do it, like a sequence. Then you look at the last element to see whether this one pair with another one. The 2 scenarios. If it's not involving any pair, then the optimal solution from ij equals optimal solution from I to j minus 1. I think you get this idea, right? You either include or not include. Or bj pair with a bp. But this a bt. But this t must be right, must be in the range from I to j minus 1, right? Or j minus 4, because it cannot be too close to j. So this is about the location of this t. This t cannot be too close to n. So this is the range, right? Then based on this diagram, you partition the space into 2 parts. One part is 1 to t. Right? So that means inside pair, you can have a more pair here. Obviously, this t cannot be reused. The t already paired with n. So this basically is from 1 to t minus 1. So in this case, I to t minus 1. That's why I to t minus 1, optimal solution. Another path is inside here. Inside here is you can from t plus 1 to n minus 1. You treat this like a new problem, right? How many possible pairing? So that's how we do it. Then all you need to do is pick the best location for t, right? Because you have many possible t. Another question, how you calculate? If you look carefully, it's not too difficult. It's just like if you can calculate all the pairing, start from the small number maybe the stretch, right? Stretch small, at least be 5. They have a 6 and 7 and 8. Then for all the section you calculate, then you can enumerate all the possibility of t. Right? So this is it's a straightforward implementation. So that's how you have some kind of loop. Loop k really means that it's kind of a distance. So this k really means that the distance between I and j. So it should be start from 5, 6, and so on. So this is really represented in the here. For example, this is I position, this is j position. So this really means a string, suppose I to j is 1 to 8. So the fact you put the 0 really means these are not eligible because they're too close, right? Too close to 6, 3 obvious, too close to 6. So you cannot fool anyone. Real consideration stuff from here, 1 and 6. After 1 and 6, you check 2 and 7. Then you check a 3 and 7, 3, 8. This is 4 and 9. But look at this diagonal line, really means that everything k equals 5, right? So that means a stretch is 5. After that, you can look at all the stretch of 6, 1, 7, 2, 8, 3, 9. Then after that, you check 1, 8, 2, 8, 2, 9. Last one is 1, 9, right? So this really means the sequence is very important because this smaller stretch one will be used in the calculation when you do recursive call. But then we do this iterative calculation. It's very simple. It's just you fill in this table, right? So you follow that, you already get calculation. So it's really surprising, simple in terms of a calculation. Obviously, when we calculate this one, we don't really put the number there. It's just using the recursion. What's a recursion? Recursion is already here, right? This is the recursion. Recursion really means that you use the, since this, the stretch is smaller than this one. So that means you can reuse the table early, which already filled. So that's how you, dynamic program is sometimes called like a table filling process. You follow a certain sequence, you fill out the table, then you're done. Okay, so that's all for this problem. Any question? I'm doing a little bit fast, but still this is not too difficult if you look carefully, right? Obviously, once you have a solution, it's easy, but if I give you, it's not that easy. So the key things for this one is that you look at the last element in this string, you check with the possible pairing of t, and this t could vary, right, the number. But we make the problem more general. Instead of looking from 1 to n, you look at I and j. So for any adjacent subsequence or subsequent, just like multiple matrix multiplication. Then you do this recursive call, because whenever you form a pairing t and n, you partition the space into 2 parts. One part is from 1 to t, another part from t to n. Then you can do this iterative process. Any discussion? So all clear? Or confused? If no, let's move to the last one. The last one is the most complicated one, not in terms of solution, but it's just so smart, like how to reduce the space. We never talk about the space requirement. Actually, most of the problem we discuss, we never mention about space for a couple of reasons. One reason is that in the past, space is important because memory, we're talking about 30 or 40 years ago. So you don't have this large memory size. But nowadays, we have. Right? The memory space is very cheap. For example, you can store all your data, email, right, using cloud, and obviously pay little money, but that's not a big deal. But we look at the one case is that the memory is kind of important for another reason, especially when it involves large data. All right. So let's look at the problem. And another related topic, computation biology. So it's a development application of data analytical and theoretical methods, mathematical modeling, computation simulation technique to the study of biological, ecological, behavioral, and social systems. So it's more than just biological, right? Like a sequence matching. It could be many other things, behavioral or social system. So we look at the one particular problem. It's called the sequence alignment. Or you can imagine this is like a DNA sequence alignment. But this is more interesting in that we always use this spelling error correction or spelling check. Like when nowadays you type very fast, and this is very important issues. Actually, I'm kind of very conservative when I use when we use cellular phone, right? In the past, probably you're not old enough. Older phones, the keyboard, they have a touch keyboard. Really means that you can feel. Like the most famous one is the I suddenly forgot what's the famous company? It's a Canadian company, right? Built this very popular cellular phone. Typing is very simple because you can feel the keyboard. So I'm kind of reluctant to use iPhone because I'm worried that when you type iPhone, when you touch a screen, you don't have a feel. How about that I type and we're full of errors? So this happened. But nowadays you can develop, there are lots of building software that is very smart and you can remember your pattern, whatever. So whenever you type something, it will automatically correct you. Right, so that's the key. So do you realize that the question is how the system will know that what things you really type? Right? So this actually relates to this string similarity. For example, there are two characters here, occurrences. The difference is that you see that the second one you have extra C, and another big difference that you have here, one is A, one is E. Then the question is which one is, what's the distance between these two? Well, it's very important. Just imagine that the first one is the one you type. The second one is the real ones in the memory, right? But you want to estimate that what's the distance? Distance means a similarity. Because the machine should be smart enough to tell. Suppose there was similarity between multiple ones. Could mean different things, right? But it will pick one that the closest distance in terms of most similar one. So why this is so difficult? In fact, it's quite difficult in the sense that we didn't realize there are two things. One concept is called mismatch. The other one is called gap. So mismatch means that the position-wise is aligned, but you type a wrong word. Right? So this is an example of this one. Actually, the easy way, you would say, oh, it's easy. You align with the first character, then the second one. But what happened to the last one? Last one, you just put a bar, which means I don't care. So this really means the last one is not match. We call a gap. But if we do in this way, because this extra C introduced, then you have a lot of mismatch, right? Mismatch. So you have 6 mismatches and 1 gap. Oh, you say, probably we should do this one, but it looks like because you know that likely you miss 1 extra C, so you miss C. So what you can do is you insert the empty space in between here. Then it's totally different. Then introduce extra space somewhere here, right? Then there is only one gap, means that one character is not matched, but all the other one kind of match except A and E. See that A and E, that one. So that one mismatch, one gap. So which one is a better one? Or we assign some kind of weight. Right? So what's the cost for mismatch? What's the cost of a gap? See, you get that, right? Or you can do another way, is that you can totally avoid mismatches. Right? So that means any characters are different, you insert an empty space. So in this case, you can see that there's no mismatch, but it'll create more gap. So you have like 3 gaps. You get that one? So you can see that the spelling check or spelling error correction is not that simple. Just for the 2 pair, there are many ways to interpret by either shift around or you insert an empty space or you just do direct matching. So I think with this example, you already get the idea, right? So the key thing is how you assign the weight to mismatch and how much weight for the gap. But that's just application oriented. So this one is the many application. We already see that. One application is in the Unix diff. So really means that Unix is an operating system, right? So then we give you 2 files. This operation will return like a similarity between 2 files. So it's the same. And speech recognition is the same, right? So you speak something, maybe mispronounce or something, then you will try to find a right word that most similar. And computational biology, same. Just imagine those numbers like RNA, the sequence, right? CGUA, and those number. Then you can do the for example, when you do your transmission or when you do reading, one particular character is missed or maybe misread, then how you do this kind of corrections. So actually this problem is edited distance concept is relatively old. You can see 1960, 1970. So we just put a penalty called gap. Penalty is delta, missed penalty is alpha, P and Q. Here is a little bit different. Really means that penalty can, the value changes depends on P and Q. And while the gap, you assign the uniform the value. The cost or determine the similarity is the sum of the gap and mismatch penalty. So that's obvious. So like this example, and all this, there's no gap. Everything is just mismatch penalty. So there's a penalty for T and C and G and A. So why you may ask, why this one have a different penalty? Because this is a likelihood that C was mistaken by T, or right, the chances. So you may have a different way. While the gap here, like a gap, this is a uniform, because this one you don't really know what's the value. So the penalty is uniform. So they have a 2 gap, 1 mismatch. Okay. So your goal is try to find a matching with the minimum cost. So this will define this similarity value. Okay. So I'm not going to go through this. The other part is just easy, right? So you just align, you can insert some extra space, which you call the gap, and that's it. Let's just look directly at the solution. The first solution is kind of simple. Is this one. Suppose you have a string from 1 to I, another string 1 to j. One is x, the other y. Right? So that means these 2 strings are not necessarily the same length, like the previous example. They're not the same length. So what you do is the same one. It's like a recursion. You compare the last 2 elements. xi compare with yj. xi compare with yj. If there is a mismatch, then you pay the penalty of a mismatch, plus whatever the minimum cost of aligning two string. Now this string, you already match I and j, right? Xi with Yj. So then the two substring is from Xi to Xi minus 1, then compare with Y1 to my Yj minus 1. All right, so already get a recursive call, already one. Then basically 3 cases, 3 choices. You either directly match, another one you say, no, I'm not going to, I leave this unmatched. A match means you insert one space, right? One space. One space means that you just match this xi with empty space from j. So that's why the index I will be reduced by 1. The index for y does not change. You get that, right? So that means you insert one extra elements for j or for y, so that x match that. But this will create a gap. Then you find out whatever the minimum cost align with I to 1 to I minus 1, whereas the other one is I to j. Then the same thing is that you can insert the other empty space for xi so that yj is matched with some empty space. Then you call for this. But you see the difference is just the index, right? So you either do no change, or you change by 1, both by 1, or you change one by 1, the other one by 1. So that's why we have this recursive call in the middle, right? The middle one means that if you directly match, you pay the penalty of a mismatch. Obviously, if they're matched, then there's no penalty of alpha. Then each index reduced by half, right? And then this one is the opposite. You insert one empty space, one string. This is an empty space for the other string. So you change only one of them. Okay. And what happens if I is 0? Really means that there's nothing here. Then obviously there's nothing to match for y. So except that you introduce j empty space to match y, right? So that's why it's called j delta. Delta is cost for this empty space or gap. Same thing for j0, you match I elements. So this is a recursive call, right? So this is no surprise, and this is how you do the cost estimation. Again, for the last 2 elements, there are only 3 choices. Match directly, one insert one empty space, and the third one is insert empty space to another string. And this is how you calculate. Again, the calculation is not that difficult. It's from I to j in general. Ij is from m to n. Suppose you have n, x is m, y is n. So again, you fill out this the value in ij value, right? Ij value from I to 1 to n, j is from 1 to n. But you have to follow a certain sequence because it depends. You have a recursive call. Right? So this is how you do that. But you do it iteratively, so you don't need recursion. That's the final one. Okay, so that's the like a similarity test based on the minimum weight cost. Any question on that? Any question? I think this one is not too difficult, right? But the difficulty is the next one, the improvement. So why we need improvement in this case is that this problem, this solution is perfectly fine if we want to match an English sentence or words. where usually mn is less equal than 10, right? Just look at your last name, whatever the last name or first name. So each word in terms of number of characters, it's relatively small. But for computation biology, that could be a disaster. So it really means that what happens if this m and n is very long, right? So like a string, this example of 100,000. Then we're talking about the space is m times n. So it's basically it's a square of that. So that means you may occupy lots of space. Occupy space means that you need to allocate that amount of space in order to calculate one particular matching. Right? And are there any solution that time-wise is okay, m times n, but you can reduce the space. Fortunately, there's a very nice solution called sequence alignments in linear space. You only need to use a linear space. And in fact, they use a concept of dynamic programming combined with divide and conquer. So far, all the examples we discussed, divide and conquer, greedy, dynamic programming, especially divide and conquer dynamic programming, we treat it separately. Right? But this is an example that to save space, you can combine both dynamic programming and divide and conquer. So let's start with some example. Actually, intuition is not that difficult. It basically, it converts the problem like a shortest path problem. So what's the shortest path problem? Really means if this diagram, if you can understand, then it's very straightforward. So you want to align x and with y, right? You see x is from x1 to x3, y is from y1 to yx. So initially there's no alignment, there's no matching. But remember, whenever you do a matching, direct matching, for example, 1 with x1 with y1, you match. And if it does not match, there is a cost for that. So this is a cost. Right? So imagine that you come up this kind of new network with a degree of our degree of 3, in degree also 3. That means corresponds 3 scenario. So what is vertical horizontal line? Horizontal line really means that I just introduce an empty space for x to match y1. So that means it's a gap. Right? So that means this whole line here means that you always introduce a gap, right? For y, then you introduce a gap for x. So the whole thing is that you're doing a pass. For example, you can go through from here, that eventually you reach this one. Reach this side means that you find the pass. Right? Pass means that you can use either gap or mismatch. Right? Gap is 2 types of gap. So then why is the shortest path? Meaning that there is a cost associated with each line. When you have a mismatch, you have a cost. And if you have a gap, there's a cost, right? So that's how we do it. Really means a cost of a mismatch I, xi with yj, that's a cost. Gap is just always delta. So is that kind of interesting? Now the problem has become like shortest path. It's a straightforward, very straightforward. But the point is not for us is to find the shortest path, but to find out the space. We want to reduce the space. So how we do that? Let's first study this recursive for solution, divide and conquer solution. It's just like a Dijkstra shortest path, but it's in a different way. So suppose we divide this one into 2 parts, right? So for example, we stop at j, particular I and j. So you just basically find the shortest path to here. this we can do. It's not that difficult. But then the question is that suppose you find I and J, this is suppose it's a partition point. How you find the shortest path from here to another one? Well, you can do that. It's a reverse. Reverse means that you start from this corner back to here. Remember when I discussed the Dijkstra algorithm last time? I said Dijkstra algorithm can be applied in a different way. You apply the Dijkstra algorithm to the source, another Dijkstra algorithm to the destination, then both sides grows. Eventually they will hit, they will meet. Once they meet, that's the shortest path. Is that correct? So it really means that you can have like you partition the network into two parts. One's grow from source to destination, another one from destination to source. But assuming that you already know the middle one, that's not too difficult. We'll see later. Right. So the key thing is here, right? So you have ij, and then you find the shortest path. Then you combine this by reversing this. That's straightforward, not too difficult. But our whole idea is divide and conquer. Divide and conquer really means that suppose you have this column, n column, right? So we divide into half, middle, the middle one. Suppose you already find a position here, which is a part of the shortest path. Or we'll talk about later how we find the shortest path. Suppose you already find the shortest path, and that's the position. Then what you can do is that the remaining part, that's the key, right? Remaining part is that suppose you find this one, remaining part is the shortest path from 0, 0 to ij. Another one is shortest path from this mn to ij. Right? So you have two different color. Then you can do a two recursive call. So inside this one, you partition again, you partition again. Okay. But that part is not really exciting. So why this will reduce the space? Because from here, you don't see this reduced space. So all this one, the high level, let's first discuss it. You find the key thing is that you from this n divided by 2, right? You find a position of the row, which is called Q, such that when you divide this one function through, this f means from this one, 0 to here, this part plus the cost from this part to that is minimized. Right? This is using DP, right? Dynamic programming. Then the conquer is just recursively compute optimal alignment in each pieces. So you have this larger piece now dividing to this small piece, right? Two small pieces. By the way, these two small pieces, the space does not overlap. So that's the key. Later, we'll discuss that. Okay. But the high level algorithm wise, it's not difficult. Right? Now let's see how we apply this one. Oh, these are new slides I added. First, I want to show you how this cost looks like. So this means that there's zero match. You try to match two words. One is called mean, M-E-A-N, match with name, N-A-M-E, right? So this really means initially from here, if you add, so this key is that for a gap, it costs 2 units. You want to find a matching, or just basic a pass all the way to here with the minimum cost. So that's the key. For a gap, it costs 2. And for a mismatch, it depends. Right? If it's a vowel to vowel, mismatch vowel to vowel, it costs 1. If it's a consonant match with a consonant, it's 1. When you mismatch between a vowel and consonant, penalty is 3. So why this penalty is 3? We know that it's less likely you confuse vowel with a consonant. Right? So that's why. Don't tell me what's the reason, or you can associate with 2 or 3 or 4. Doesn't really matter. You get that, right? So you see that if you do it horizontal or vertical, like this example, you add 2, 2, 2, 2, 2. Okay, this one does not go anywhere. It just stop there. Or you can do have a gap, then you do a mismatch. This does not go anywhere. So the only way you can go is through this way. So first is a mismatch, then the gap. Then this one actually is no gap because it's a perfect match A with A. Then this one is a mismatch of 1, mismatch of 1, M and N. So that's how you would maybe like mispronounce. The last one, another gap. So the total cost is 6. Right? So this is the. So the key thing is that how can you save memory? So we need to introduce a new algorithm, but it's not too difficult. It's the same algorithm. The key is that suppose you want to develop an algorithm just to find out the value of the optimal assignment, really like a shortest path, but without specifying how you find it. Then the A means that the original matrix, right? This A entry can be collapsed into a B with only two rows. So this means that the B, see I, and 0 and 1. What this really means that you need to go back to the previous, this one here. Look at the J value. So this is the key, the J value. Right, when you do a recursion, you see the difference between J and J, another one is J minus 1. So that means that for each call, recursive call, the J value differ only by 1. So that means in terms of memory, you just need the 2. That's why you use the 2. But the question is that what happened to the next one? When you move down to the next one, like a J minus 2, then you can swap these 2. So that's the idea. But anyway, at this stage, we only need to calculate its value. So key thing is the value. So I'm not going to go into detail. You already kind of know the idea. So you have like a 2. One is a 0 and the other one is a 1. So you don't need like a multiple. You only need 2. So that's how you save the space. Then once you find it, so this we call space efficient assignment. Space efficient assignment. This assignment, by the way, does not really tell you how to do the matching. Matching means a gap or mismatch. It just tells you the value, the cost. So that's key. Only calculate the cost. Why you need to calculate the cost? It's described here. Is that remember when we partition the space and this column is n divided by 2, right? N divided by 2. Now the question is that which position will correspond to the shortest path? Is this from the first row to this one, or this one, or this one, or this one? Right? So at this stage, we don't really care about how you reach this shortest path. We only care about the value for all this 4 value. Once we get the value, then we know how to do the partition. So that's the key, right? So that means we use this space efficient assignment to calculate the value for each row. And obviously the other one is called backward, called the back space efficient assignment. So it means from this one to this. So you need to calculate its distance. Then you add these 2 distance, right? Add together. Then you know the total distance. But you have to check for each row. So that's why you need to apply this each row. That's how you get to this space. For initially it's M and this is N. Why this one? Because you see how many rows, right? How many rows? But for each calculation, we need 2 rows. So this is how we do it. But now the challenge is that suppose you find this one, And later, internally, you have to recursive call this one. Again, you need to partition the space into two, right? Column-wise. But here you need another space. So the key thing here is the recursive call is sequentially. So you can reuse the working space, right? So you think a little bit. You can reuse the working space because they don't conflict with each other. So this is how you do it. So let's look at this algorithm. The algorithm really mean this is m smaller than it's just direct calculation. The key thing is this one. Call this one called space efficient assignment and call backward space efficient assignment. This main purpose to find its value of a cost from 0 to q and also from the n to q, this value. Then once you find this value, you add these two together. So you know what's the cost, right? You find a particular row such that these two parts add together is a minimum. But once you find the Q, now you do serious business, right? Then you can partition the two space of this part and this part. Okay. By the way, why this again the space is n, right? Remember this calculation for this part. You see this b. B is a 0 to n, and this one is 0 and 1. Right? There's only 2 units. And this recursive call you apply is sequentially. Right? You reuse the working space. Obviously, this is a little bit more, much more involved than the previous one, but just try to save the memory space. Okay. Probably that's the only one we care about the space so far. Then there is also the analysis part. It's also a little bit more involved. Is that when you partition into two, right? Remember, you partition this into two. So you have like a two recursive call here. And then for this all kind of calculation here, you want to find the Q value, the cost is Mn. If we do this kind of estimation, the total cost is Mn log n. So this is kind of like a bad news. Remember in the previous solution, without considering the memory space, the runtime is m times n. But in reality, this one can be reduced. This estimation is not accurate. The reason we assume that this size, two parts, is actually the same. In reality, it's not, right? The reason is that it depends on Q value. You see, this Q value have 2 rows, but this portion is maybe also multiple. So it depends on the Q value. The total you have n rows. So if the first one has a Q row, then the next one is m minus Q row. So if you replace this one by more accurate calculation, which is this one, then you can do, you can prove it by the induction process. Maybe this is actually a very good exercise. So how you do this kind of induction, right? So this is a little bit more involved, but not too difficult. Again, this induction. You assume that your total cost is CMN, right? So you first establish this one, CM2 and 2N, and CM and CM. Then you do the base, the induction hypothesis. You substitute the number by this, right? Then eventually you get the 2CMN. So that's how you get the result. So the key, you get this 2CMN. So that means with a little bit more careful calculation, you find out this recursive solution does not increase the computation, but it does save the memory. But again, this is a little bit more involved because it involves divide and conquer, recursive call. While the previous solution only use iterative solution, which is very straightforward, right? So there's always a trade-off. You get a simple solution like this. Is a very simple solution and intuitive, but they use more space. While the other one use recursion, and it saves space, but programming is a little bit more involved. Okay, so I think with this we exactly finish this one. We haven't discussed this, so I would like to. So what do you think? You prefer to submit one day early so I can grade them and get back to you? Or, again, this is not mandatory. Or you can submit it the same day we have a midterm. So I still set a deadline to Wednesday, midnight. How's that?
I think that's good. Yeah.
Yeah. I mean, give us still an option, right? So probably I will still grade on Wednesday morning and return to whoever you submit. And if you cannot finish, I will grade it on Thursday together with midterm. To be honest, I still haven't thought about the type of question I will give. This time I made modify it a little bit to give less stress. Means that if I give a question like homework, it's kind of very involved. So I may come up some example, maybe modification of homework problem, or in some cases may I have multiple choices, right? So that means that I don't want the situation that you know all the material, just get stuck on one particular problem, and that problem costs you, for example, 30 points. And then that's the. So the key thing that for you to prepare is that I give you 36 questions, right? So you make sure that you understand all the 63 questions, plus all the example in the slides. I mean, it's lots of preparation, but I think that's the only way you really learn the algorithm. Any other discussion?
So you mentioned that you will give us those questions by Friday, right?
Yeah, but that format may change.
Okay,
That's a lot. I mean, 2 years ago. Yeah, I will give you. Okay, so if we don't have any questions, so let me stop the recording.
Professor, I have just a quick question regarding this last induction. So we proved that this TMN was less than or equal to CMN, right? But shouldn't we find a C value for which both the base case and the induction step hold?
No, you don't need to.
So we can have like a constant plus times any kind of multiplier. So the constant doesn't need to absorb that multiplier. Right?
Oh, no, and since you ask, let me check. Right. So
because my logic is then the through induction steps that that multiplier will grow and can become exponential if we don't absorb it into the constant.
So let me see what's your question. You mean this one, right?
Yeah. So the inductive hypothesis. We need to prove that. Okay,
okay. You need to prove that.
So we don't want to prove that it's less than or equal to CMN. Okay.
It's a 2C CMN.
Okay. Is there
so
any reason
that's a challenge, right? That's you guess it's a 2. If you put a 3 and then 1, that's different.
Yeah. Okay.
Yeah, you need to absorb that. That's why you have to use.
Yes, exactly. That was my question. I thought that we made like less than or equal CMN and then we proved to CMN. Okay, this makes sense. Okay, thank you.
No, that's the trick for all the not just for this problem, for general, right? So how you guess this the coefficient?
Yeah, and how we absorb it as well.
Right. Because otherwise you never prove.
Exactly.
So you may have a run into situation. Oh, this is not correct. Then you have to guess another one. So. But probably I will not give you that kind of tough questions. Yeah. Okay, let's stop now. Let me see. I need to stop recording.